confirm that you are hearing us. It would be appreciated. Thank you.
Bruno, we can hear you.
Oh, we can hear you. No problem.
Thank you. Actually, I made a mistake. We have not started again the working group is covered. And we halted. We did not start. I didn't check because there was an issue. I can say the correct message. Shall we start? I can run the slides because I've already started.
So go ahead.
Okay, good morning, everyone, or good afternoon. You're in Spring Working Group. We have a full session today, so we're going to start now. Remember that the session is being recorded, including in video if you're in the room. This is the note well. You need to read it if you haven't read it, especially if you are contributed. So this is information for IETF 115. So if you are in-person participant, you need to sign in using Miteco Lite. This is being used as blue sheet. And also this thing being used to queue on the bike. So you have to enable queue on Miteco Lite before going to the mic so that we can handle a single queue for both local and remote attendees. But obviously keep your audio and video off if you are not using the light version. Also something very important, everyone needs to wear a mask anytime except if you are actively drinking, eating or speaking at the mic. This is very important. This is going to be checked, including during the meeting. So please make sure you have a mask. If you're remote, make sure your audio and video are off unless you are actively presenting. And usually a headset is a better audio quality. In terms of minutes, we're going to use a collaborative tools, which is available at the following URL. You're welcome to help to take notes. At least please check and correct your name and comments. You can do so. IETF is moving to a new wiki system. So Spring Working Group has moved to the new wiki. It's available at the following URL. The wiki has been slightly reorganized. It has also been updated. So thank you, Shopping, about that. You're welcome to check whether the content is correct during the migration. Especially, you can check whether your request for last call or adoption call is still there and still correct. Okay, so since July, we have adopted a new policy in the working group. So we now mandate an implementation section in the draft, at least before working group last call. This section is based on BCP 200.05, which is about improving awareness of running code with the implementation status section. We have a bit more specific items. We request all items identified in section 2 of the BCP to be filled. You can put not known, it's fine, but just to check that it's not lost. It's not blocking for progressing to ISG, but we do request best effort. So you can fill non-report or does not apply, but something needs to be written. We also ask for a statement that the implementation is compliant with all must and should in the specification, and if not, which one are not followed. And as per BCP 205, the section will be removed before RFC publication. So you can check the full policy on the wiki. But it's just a reminder, it has been discussed on the list. In terms of document, so my mistake in the slide, the working group last call has not been started. Actually, we started, but we stopped it because the implementation section wasn't there. But we are about to start again the working group last call on SR verification segment. So please review and comment. It's important for our specification to be supported by the group and to be reviewed from a technical standpoint. So it's very important. Otherwise, the draft would not progress. In terms of last call, we have an IETF last call just started on MPLS pass segment. And we also have a document submitted to ISD for publication about NSH integration with segment routing. So that's all for document status. This is the agenda for today. We have a full agenda. So please stick to your allocated time, which include time to present and time to discuss. Is there any comments or bashing on the agenda? Anyone remote? No. So if not, we're going to start with the first being Rakesh for MPLS network action.
Good morning, everyone. My name is Rakesh Gandhi from Cisco Systems. I'm presenting the MPLS Network Action Header and Coding Solutions draft on behalf of the co-authors listed. Many thanks to all the authors for working together, collaborating, and producing this converged unified solutions. Really appreciate it. Next slide, please.
Sorry.
Next slide. Yeah, many thanks to all the contributors. They've been co-authors as well, but with the limit of 5 authors. So many thanks for all your inputs and contributions. Next slide, please. Next slide, please. So in agenda, we have this being presented in PALS tomorrow. There is more time allocated for this presentation in PALS. There will be good discussion on it as well. And we're just presenting in spring because of some SR MPLS implications on it. The scope is, we'll look at the scope, the solution that's presented in the draft. We have reserved opcodes. There is some ordering. There's some good discussions happening on the action ordering, backwards compatibility, and the next steps. Next slide, please. So the scope of this draft is for the MPLS encoding solution that's in the label stack. There is another draft for the post stack highest draft. So both of them together form the complete M&A solution. And the scope is to meet the M&A requirements and the framework that's already adopted by the MPLS working group. Next slide, please. So there are 2 parts to the solution. One is the network action, the substack header, and the second is the action encoding. The header is basically a BSPL label indicating that there is a substack there with its encoding parameters like the scope, the ordering length, and whatnot. And the action is basically a TLB. So opcode length and the ancillary data is the value. Next slide, please. So the header, as mentioned, there's a BSPL, there is a length of the header for the, so a lot of work has been gone in defining this encoding for easier parsing, especially in ASIC. So there is a length, the scope is there if you want to do on the endpoints or hop by hop or on select nodes. There is some discussion ordering. There's a bit that says it must be executed or the order is specified or it's an optional. So next slide, please. And the second part is the action encoding part, which is a TLV. So you have opcode, the data, and the length of it. So if it's not recognized using the length, it can be skipped. There is unknown opcode handling. So if you don't recognize it, there is a way to specify either a skip and go to the next one based on the length, or drop the packet, or just forget about M&A and just forward the packet. So this is basically, if you can see this as a toolkit, and how application will use this toolkit, it will be up to the applications. So the programming aspects of it and all the parameters are in the solutions. Next slide, please. So there is a substack per scope. So for the hop by hop or select or end-to-end scope, there is a substack. This is defined to make the parsing and processing easier on the midpoint nodes. Next slide, please. So we have reserved some opcodes. There are 4 or 5 of them. First one is to say where the offset is for the post-stack data. So this is to allow the GSCH kind of existing data or header to be carried. Another one is an opcode to just, if you just want to carry the flag-based actions. There is a third one is for the flag-based actions with data. And then there is another one to carry the post-stack network actions as well. So that's on the next slide. Yeah, so we can skip this as well. Yeah, and there are 2 special opcodes. One is the opcode 127. So it's a 7-bit opcode in case we run out of it, unlikely, but there is a way to extend it. And 126 is if there is no in-stack action and there is only post-stack actions, 126 is reserved for it. Next slide, please. So there is some discussions about ordering how it should be executed. So there's an OB defined. If it's set, then it must be executed in the order that's encoded. If not, then it's based on how the application defined it. There is some discussions about what should be done in stack or post stack. So there are some flag based, so how that should be executed as well. So there are some examples in the draft on what the authors think can be done. Welcome your comments on that. Next slide, please. So this is about ordering between in-stack and post-stack as well. Next slide, please. So there is a lot of brainstorming and thinking went in to make sure the solution is backwards compatible, especially if you're only going to do the end-to-end processing or end-to-end M&A. We don't want to upgrade the penultimate node or midpoint nodes. It should be transparent to it. Make sure the ECMP is not adversely affected. Make sure that it doesn't alias with existing reserved BSPL. It can coexist with GSCH. So a lot of thinking has gone in, but there could be something. So if you have feedback on these aspects, please let us know. Next slide, please. We'll skip the advantages. So at this point, I welcome your review comments and feedbacks. As mentioned, this is a converged unified solution among all the authors. We received lots of good review comments, and we are addressing these comments. Some cleanup is required. There's some discussions on the scope and ordering. So all the aspects that we presented today, let us know if you have feedback, comments. And that's all I had.
Grand Mirsky Erickson. So you mentioned that the authors paid special attention to end-to-end operation of M&A. So basically when M&A is expected to be operated only at egress. But my understanding is that there are other options. There is a hop by hop, and there is what's called select. Given it's currently indicated in very high level of encoding, do you see that different modes can be combined together? For example, so some functions like IOM being requested to do hop by hop, while, for example, generic flow indicator is clearly end-to-end.
Yes, definitely. So there is a substack for hop by hop, and there is a substack for end-to-end. Only requirement for backwards compatibility is that the M&A BSPL, if it's exposed or under receive packet at the node receiving it, and that does not understand the BSPL, it may drop the packet. So that's the only constraint for the backwards compatibility. So the ingress or NCAP node needs to make sure that along the path is never received, BSPL is not at the top on the received node that it cannot understand.
Well, that was not really my question. Let me rephrase. So, for example, imagine that because of maximum stack depth along the path, we can put hop by hop and end-to-end at the bottom of the stack. So to do hop by hop and end-to-end network actions with the current encapsulation, do you see it's possible to do it under one special purpose label, or that will require two special purpose labels, so two network action substacks?
So the one special purpose label, we can have multiple copies of the substack, and we can have copies with different scope. So you would have one substack with hop by hop scope, and another substack with I2E scope. And hop by hop substack will contain the IOM, and the second substack with the same BSPL will have the flow identifier for I2E.
Okay, thank you.
Okay, thank you. Any?
No, that's
No.
Many thanks.
Thank you. Now we'll move to next presentation. SRv6 for interlayer network programming. Presenter being Johan.
Mr. Chairman, is my voice okay?
I can hear you. I'm going to share your slide. Yes.
Good morning, everyone. This draft is on the topic of SRv6 for interlayer network programming, and the authors are from Huawei and China Mobile. Next slide, please. First, I will introduce the background. Operators usually have a multi-layered network. The layer 3 is normally IP-based technology, where different technology could be used for the underlying layers. For example, layer 2 and layer 1. The cross-layer network programming and optimization is expected. It is considered more efficient compared with the independent planning for each layer, but it's also considered more complicated. SRv6 enabled network programming by encoding network instructions in IP handler, but currently only the network instructions related to IP layer are defined. So we come to use SRv6 for the network layers under IP. So we think SRv6 can be further extended to achieve the seamless interlayer network integration between IP and the underlayer layers. So this document describes the use cases for the interlayer network programming, and we propose a new SRv6 function for this purpose. Next slide, please. We give 3 use cases for the interlayer programming. These 3 scenarios are very common and widely used in the operator's network. First case is IP and optical network integration. In many scenarios in the network, the underlay of IP network is the optical network. But in some cases, the optical parts and the IP parts may not be one-by-one mapping, so the redundant optical passes may not be fully used by IP layer. Secondly, the optical passes may exist between non-adjacent IP nodes, so it's not visible in the layer 3 topology. The second case is the IP and MTN integration. The MTN is Metro Transport Network. It's a new technology and has been defined in IETF115-SPRING-20221108-0930. The MTN parse layer uses TDM switching in the intermediate nodes to avoid hop-by-hop IP packet switching. So MTN nodes can support both per hop IP forwarding, and it also supports MTN parse cross connect. The traffic can be carried using IP parse, MTN parse, or the combination of the two, but currently SRv6 only can be used for the IP parse programming for the MTN network. The MTN parse is not included. The third use case is traffic steering to layer 2 bundle member link. Each member link is a layer 2 connection without layer 3 adjacency. So if we want to choose one specific layer 2 member link, we need a new function. Next slide, please. Also, we propose a new SRv6, which called AND-XU, in order to solve the interlayer programming in the use cases. This endpoint with underlying cross connect is a variant of the AND-X behavior. Its main purpose is for the interlayer programming and traffic engineering. The AND-XU seed is associated with an underlay interface which connects to one or more underlay links or connections. And the line 15 from the SRv6 and progressing in the current RFC 8986 is replaced by the following. Forward the packet through the underlay interface associated with seed S. Next slide, please. In this slide, we give an application example to use the AND-XU in IP optical integration. In this figure, we can see there is an IP network. The underlay is the optical network. The node P1 to P8 is the IP nodes, and the node O1 to O6 is the optical nodes. If we want to set up a packet transmission connection from P7 to the right P8, with normal segment routing solution, we can find the seed list in IP network is P7, P1, P2, P3, P8. But assume there is an optical parse O1, O2 to O3 exists in the optical network. We can use the AND-XU seed to P1 to steer traffic to this underlay optical parse. So maybe we can provide a lower latency compared with the normal IP parse. Therefore, the IP optical interlayer path can be created with the seed list. The new seed list is P7, P1, and XU from O2 to O3, then go to the P3, P8. Next slide, please. We give another example in this slide. It's an application of AND-XU in IP MTN integration. We can see in the figure. In the figure, the operator owns both MTN network in the metro area and on the IP network in the backbone area. But for the MTN nodes, it builds two separate network layers, the layer 3 function in the topology and the MTN parse topology. The nodes in the MTN domain support both the layer 3 forwarding and MTN parse cross connect. So we can use AND XUC to be allocated for each MTN parse. So we can create a seed list with AND XU to end-to-end parse with layer 3 and MTN segments. In this solution, we can flexibly select MTN parse and layer 3 in all the networks. Next slide, please. So in conclusion, we think the interlayer network programming is a significant requirement and suggest to study and define the endpoint function for this application. And any comments and feedbacks are welcome. Thank you very much. That's all.
Okay, Sasha, you're up first.
Hi, I'm Sasha Weinstein from Ribbon. Can you please show again the slide with the, no, one more, yes, this one. I have a question. As explained, the optical path between P1 and P3 is not an IP path. My question is, when P3 receives an IP packet from P7, I think, how does it know which layer 2 encapsulation should be pushed on this packet before it is sent via the optical path? Because without this encapsulation, P3 most probably wouldn't recognize the packet as an IP packet and wouldn't be able to forward it via the IP path to P8. Normally, P8, if the path were an IP interface, P1 would try to resolve P3 IP address or something like that using ARP or neighbor discovery. But since the optical path is not an IP path, such resolution seems impossible.
Huyan, do you have any comment on that?
Can I answer it?
Oh, well, Ran Chen, you're next.
Can I? Okay.
Go ahead, Luyan. If you have a response to Sasha.
Yeah. Okay. Hi. We agree with the use case of SRv6 interlayer network programming and requirements. And thank you very much for your research on this work. And we also have similar proposals. But we define the new SRv6 and the BXC behavior for interlayer network programming. The SRv6 and the BXC function mechanism has been implemented by ZTE, and China Mobile has successfully completed the basic verification of this function. Hope it can catch you and the working group attention. Thank you.
Ketan, go ahead.
Kind of follow on to Sasha's comment that whether the optical path is IP or not is, I think, not clear. But N.X SID, which is in RFC 8986 network programming, can be used for layer 2 bundle member SIDs. And therefore, I mean, I don't see any reason why we need a new behavior. It can be used for this optical link as well, for steering into optical path as well. N.X, the existing one.
Okay, thank you, Ketan. Jidong, your turn.
Hi, Zedong from Huawei. And firstly, I'd like to respond to Sasha's comment on the whether P3 can correctly receive the packet and forward it. I think it's a good question. Whether how to resolve the IRP or the layer 2 information. Seems this draft currently does not cover that details, but perhaps we can consider to distribute that kind of information through some control plane. That is the reply. And to the comments from Ketan, our understanding is the current end.x behavior is correct, explicitly defined for the layer 3 adjacency, and that kind of information are used to build the layer 3 topology and the forwarding path in the layer 3 network. We define this end.xu to separate it from the layer 3 topology so that for some network behaviors, we don't want to mix the layer 3 adjacency with the underlay links so that we can have different path computation for different kind of service. So this is the purpose to distinguish these two behaviors. Okay.
Okay, we'll move on to that.
I have
Seems to
put
have
it in the
cleared. Somebody was trying to say something. I couldn't tell who. Okay, we'll move on to the next presentation. Thank you.
Hello, can you hear me?
Yes, we do.
Yes, thank you. I'm Yisung Liu from China Mobile, and today I will present the encapsulation of BFD for the SR6 policy. This is the first presentation of this draft. Next slide, please. Okay. When we use the BFD session to monitor the SRA6 policy, and as we know, SRA6 policy has 3 levels, and the BFD session runs associated with the segment list level. And when the BFD session done, the associated segment list fail, and the traffic will stop forwarding and with this specific segment list. When all of the segment list fail of the active candidate paths, and the traffic will switch over to the backup candidate path, and all of the candidate paths fail, and the policy failed. When we the second is that what the choice of the address for the BFD. Here we give the 2 types of the BFD, SBFD and the UBFD. UBFD means that we use the BFD echo function and the U-turn on the reflector. And when we use the SBFD, the head end address, we can use the IP6 address of the head end, and the tail end address, we use the endpoint of the SRv6 policy or specified by the local configuration. And for the UBFD, the head end address, we use the IPv6 address of the head end. We'll use the routable or non-routable. For the tail end, we must use the routable IPv6 address of the head end. Next slide, please. And we have the 2 modes of the encapsulation of the BFD packet, and the difference between the SRH, how to encapsulate the SRH. And for the transport mode, the SRH is inserted after the IPv6 header. And the tunnel mode, we have the outer IPv6 header with the SRH, and the inner is for the BFD packet, like the plain IPv6 packet, steered into the SRv6 policy. Next slide, please. And next slide, I will give the details of these two modes for both the SBFD and the UBFD. And when the SBFD in transport mode, we encapsulate only one IPv6 header and the SRH. And for the SL0 position, should be the SRH6 seed or the IPv6 address of the tail end node. But sometimes the last segment of the segment list in the SRH6 policy does not belong to the tail end. It can be a n.x segment of the penultimate hop or bounding seed. So in such cases, we will add IPv6 address or SRv6 seed of the tail end node. And the last segment will put in the SL1 position in the SRH. Next slide, please. When the SBFD in tunnel mode, we encapsulate the inner IPv6 header with a BFD packet and the outer with the IPv6 header with SRH. And at the same, the SL0 position should be the SRv6 seed or the IPv6 address of the tail end node. And if the last segment of the segment list in SRv6 policy does not belong to the tail end, and may be n.x, but this n.x without the USD flavor. If it has the USD flavor, it can decapsulate one at the penultimate hop. So if we doesn't have the USD flavor or it is the binding seed, we should add IPv6 address or a seed of the tail end node in the SL0 position and put the last segment of the segment list in SR6 policy in the SL1 position. So next slide, please. The next two slides about the UBFD. When the UBFD in transport mode, that is simple thing, and only one IPv6 header is used to encapsulate the echo packet. And for the SL0 position, we use the SRv6 seed or the IPv6 address of the head end. And when the echo packet arrives the tail end, it will use the destination address at the SL0 position that is the head end node address. Next slide, please. When the UBFD in the tunnel mode, we encapsulate the inner IPv6 header and the outer SRv6 encapsulation, and the destination of the inner IPv6 is the address of the head end node, and the outer IPv6 header, we use the SL0 position should be the SRv6 seed or the IPv6 address of the tail end. And that is the same scenario that if the last segment of the SRv6 policy segment list that if the seed is the n.x segment of the penultimate hop without the USD flavor or a bounding seed, we will add the IPv6 address or seed of the tail end in the SL0 position. So next slide, please. That's all. Thank you. Welcome for the questions and comments.
Okay, Greg?
Greg Nursky Erickson. A couple of questions, but probably their first question is, what's special on encapsulation so special for BFD? Because I think that you explain different modes of SR encapsulation and SR modes, but I don't see that it's different from encapsulating payload and services that to be monitored using BFD. And I cannot find anything that is specific to BFD being used over this SRv6 modes.
We just work on the how to encapsulate the BFD packet in the SRv6 policy. It may be have minor difference from for the normal data packet.
But if you if you suggest that BFD should be encapsulated differently from the payload, then how you guarantee that BFD will follow the same path and will be treated the same as a service that you're trying to monitor? I see that there is some contradiction. So you believe that BFD has to be encapsulated differently into a SRv6 policy compared to their payload. But then the question is, if that's the case, then what are you monitoring? Because if you encapsulate differently on a SRv6 level, then the packets would not follow the same path.
Okay, I think this probably needs to go to the list. We're a little short of time. I mean, I think, Greg, you've got a good question, but we need to take it to the list. Shraddha, you're next. Shraddha? Yes,
Hello.
go ahead.
Yeah. So the question I wanted to ask, it's not clear why you're defining two different modes like transport mode and tunnel mode. It seems like all the scenarios can be satisfied with just one mode, for example, transport mode, and it can detect the liveness of the segment list. So can you explain why you define two different modes?
Sorry, I can't hear very clearly.
Okay, I will post my question on the chat. Thank you.
Okay, thank you.
Hi, can you hear me?
Diane, go ahead.
Yes, can you hear me?
Yes.
Yes, my question is, why can't the SPFD packets take the use the standard SRv6 programming? Or is there anything special that's being done in this draft other than using the standard SRv6 programming?
We just use the standard SRv6 programming. We don't change anything of that.
Okay. So what would be the benefit, I guess, of this draft? What is this draft adding outside of SRv6 programming that would need to be standardized, I guess, that's special outside of normal behavior of a packet, I guess, that's being that's being monitored from the head end, to the tail end?
Okay, Jeff, go ahead.
Jeff Haas speaking as with the BFD chair. Yisong, your presentation was clear, thank you. This comment is primarily addressed to the Spring chairs. We're currently tracking 5 distinct documents for BFD out of Spring. 1 is adopted, 4 have not been. The documents are substantially the same in many respects. This is part of what's been commented on in the last several speakers. My suggestion would be to the working group that rather than having 5 distinct documents, since the majority of this stuff is overlapping technologies with specific examples for a specific technology, SRv6, SRv6 tunneling, please consider taking one of the documents and simply having an individual encapsulation example for each of them, since the procedures are largely the same. So it'll probably save yourselves a lot of grief, and when things come around to being reviewed by BFD, for your last call process, we'll simplify things.
I can certainly understand why you'd prefer not to have to review 5, and we'd certainly prefer to see the various authors pulled together so that there's one set of review in spring as well. Thank you, Jeff.
So next is segment routing-based solution for hierarchical IETF network slices. Presenter is Liang.
Okay. Hello everyone, this is Lian from China Mobile. I'm going to talk about the topic of segment routing-based solution for hierarchical IETF network slices on behalf of all the co-authors. This draft has been presented in TSWG on 114 meeting and is suggested to present to Spring also, because the solution is based on the segment routing. So we also look forward to your comments and want to get your opinions on whether it can be moved forward. Next, please. The concept of the hierarchical IETF network slices is based on the IETF terminologies, network slicing, IETF network slice, and network resource partition. The hierarchical IETF network slices describe the network slices which can be further sliced or combined hierarchically. For example, one of the possible scenarios is that an industry slice needs to be divided into multi-customer slices. So generally, the idea of the draft is to propose a two-level hierarchical IETF network slices solution based on the segment routing. Level 1 network slice is associated with the flex algo with dedicated sub-interfaces. And the level 2 network slice is realized by using the SR policy with additional NRP ID on data plane. Next, please. This slide shows the topology and the traffic forwarding of the two-level hierarchical slices. The level 1 is associated with a flex algo, and the traffic is steered into the flex algo passes using the prefix seeds or SRv6 locators. And the level 2 network slice is associated with one or a group of SR policies under the level 1 NRP. And the traffic is steered into the SR policies. Next, please. The network resources is also partitioned in a hierarchical manner. Taking bandwidth resources as an example, the level 1 bandwidth is guaranteed by layer 3 subinterface with dedicated bandwidth. and the prefix state or SRv6 locators is used as a data plane identifier. The level 2 bandwidth is guaranteed by queues with dedicated bandwidth under the layer 3 subinterface, and the NRP ID is used as the data plane identifier. Next, please. About the relationship between the NRP and the slice, actually, each NRP, either level 1 or level 2, both can be used to support one or a group of network slice. So it is compliant with the IETF definition. But here, for the example, when we actually deploy it's much more complicated for level 2 NRP to be mapped to multi-slices. So in actual scenario, and we think it makes little sense since the resource is already finely divided as previously described. So here, for the example, the level 2 NRP to slice is shown as one-to-one. If the multiple to multiple scenario that exist, we think that the solution also it can meet the requirements. Next, please. This is one example for the whole solution from the bottom up. The physical network is divided into two NRPs through the flex algo, and each NRP is mapped to one slice. One is for education, and the other is for the healthcare. And the corresponding flex algo ID is 128 and 129. For the education slice, there are two customers, University 1, University 2. They have different access points and interactions. For healthcare slice, there is only one customer. So for the second level slice, there is only one slice. Next, please. Based on the topology previous, the resource partition is like this slide shows. For PE1, the physical interface 1, there will be two sub-interfaces, and under which there will be two or one queue respectively. This is for the second level slice. For physical interface 2, there will be only one sub-interface and one queue under the sub-interfaces. From this picture, all the sub-interfaces and queues are associated with the dedicated bandwidth, which can guarantee the slice resource. Okay, next please. This is the last picture, which illustrates the traffic forwarding. The final result is that for the normal education traffic, it is encapsulated with the end state and also associated with the specific flex algo, and it's forwarded through the layer 3 subinterfaces. And for the specific traffic from University 1 and University 2, except the IPv6 header and the SRH, the encapsulation also includes the additional NRP ID, and the traffic is forwarded through the queue and the sub-interfaces. Okay, that's all. Next, please.
Okay, just a moment before we go on. I was looking at the room and I saw a couple of people who don't have masks on. Masks on over your nose and mouth, please, unless you're eating. Thank you. You may continue.
Okay. Since it has been presented in TIS and there is no objection received, so we also look forward to your comments from Spring and also want to know if we can move forward for this draft. Thank you.
Okay, Ted Hardy.
Ted Hardy, Cisco, thank you very much for this very interesting draft. I have three fairly quick questions. The first in terms of, just to confirm my understanding, this is an informational draft that requires no protocol changes as far as I could see. So I'm not sure what work you're asking Spring to take up, and a clarification on that would be useful. Second, looking through the draft, it looked like the hierarchical nature of it would normally allow you to have one level of the hierarchy managed by SR and another level of the hierarchy managed by something else. In your university example, you might have the overall set of universities, those resources in a slice that was being managed by SR, and some, but not all of the slices for specific universities being in either SR or MPLS or something else. And I wanted to confirm whether you thought that that was possible in the approach you're taking, or whether the linkage to the underlying NRPs made that impractical. And the last question was, this is obviously very early work, 0.0. I didn't see any IPR disclosures for it, but I wondered if the authors knew of any that were in preparation. Thank you again for the interesting draft.
Okay, thank you for your comments. I will try to answer your questions. If I cannot answer it clearly, welcome to move it to the mailing list. First, about the solution, I think it's an informational solution. Yes, you are right. And there is no other extensions on protocols or
Leanne, could I interrupt your session? Gian, I think your mic is on and we're getting some weird effects by that. Leanne, could you go on?
Okay, it's okay now?
Yeah, the problem is fixed. Thank you.
Okay. Sorry. So I'll continue. Because there is no other extension on this solution, so we just propose this to check whether the solution, if there is any conflictions with the Spring opinions. So we think it's an informational document. The second one about the two-level hierarchical slice, I think the first level we use the flex algo is for the control plane. And because of the limitation of the control plane, it's very difficult to realize the multiple slice. So we proposed the second level slice, which is from the forwarding data plane. So the second level, I think they are also based on the SRv6 segment routing, because we combined it with the SR policy or the SRv6 packet forwarding an RPID. such as. I think the total solution is related with the SRv6. The second one, sorry, can you repeat it? I
Thank you.
forget
It was
it.
just a quick question of whether you knew of any IPR disclosures in process.
No, I am not aware of any IPR disclosures from now on.
Thank you again for both your answers and the interesting draft.
Okay,
Guyan?
if I can.
Yes, can you hear me?
Yes, we can hear you.
Okay. Yeah, I just had a question. You know, this is a very interesting draft, and I was wondering, as far as the hierarchy, is there, in your examples, you had 2 layers of hierarchy. Is it possible to have more than 2 layers of hierarchy? As well, I guess with the semantics of the draft, is there anything special that's being done other than what's defined in that's part of segment routing, the standard? Are there any special IANA requirements related to this draft? Thank you.
Oh, thank you very much. It's a good question. We also have thought about it, but from now on, for China Mobile, the real scenario is just a 2-level slice. For example, I think different business units with the operator, government affairs department or enterprises affairs department. Under this, there will be different users. And another example for the operator, we think for China Mobile, there are several sub-operators located at different provinces. They also want to manage their own provinces' business independently. So I think this scenario is very special for China Mobile operator. We also need the 2-level hierarchical slices.
Falling behind schedule.
Thank you.
Thank you.
Okay, we need to keep moving. We're starting to fall behind schedule, folks.
Okay.
So next is SR Pass MTU for SR policy. Guyan speaking. If you could try to speak closer to the mic, Guyan. We're not hearing you very well every time. Thank you.
Okay. Give me 1 second. I'm just going to try to make an adjustment to my mic. If you could let me know if it sounds any better. Does that sound better?
No, but that's okay. Thank you.
It doesn't sound any better. Okay. All right. I'll just try to speak a little bit closer to the mic.
Thank you.
Hi, my name is Guillaume Mishra. I'm with Verizon, and I'm presenting the draft SRPMTU for SR policy on behalf of co-authors. Next slide. So a recap, some history as to how this draft came to Spring. So during the adoption of draft PCE-PSEP PMTU, a need for a document in Spring was requested and confirmed by both the PCE and Spring working groups. So an IDR document was adopted in April of 2020. A discussion was brought up by Cathan that the concept of path MTU for SR policy and its applicability should be first defined in the Spring working group before we introduce signaling aspects in BGP. As a result of the PC PMTU extension adoption call, the draft PSEP PMTU was maintained only protocol-specific extensions of details, while the SR policy path MTU definition framework was to be developed in the Spring Working Group as a standards track document to ensure vendor interoperability related to SR, PM2 concepts, and computation details. This topic came up as a critical issue to be addressed during the IDR Working Group 2020 BGP-SR Policy PM2 adoption call, and now again during the PC Work Group 2022 PM2 adoption call, as mentioned above. And due to the criticality of solving this issue related to handling fragmentation and fragmentation avoidance procedures using SR PM2. Next slide. Updates from revision 0 to revision 1. So mostly cleanup. There was an update as well on the security consideration section. So the addition of the SRPMTU constraint information can be sensitive in some deployments and can be used to influence the SR path setup and selection results which results in an adverse effect. The protocol extension that includes the SRPMTU must take this into consideration. This document does not define any new protocol extension and thus does not introduce any further security considerations. And then as well, another update was that section 3, the SRPM2 enforcement reference to PCEP extension to handle PM2 draft was also updated. Next slide. So next steps, we would like to get some feedback on some critical aspects of this draft from the working group experts. One of the questions that we have as far from us authors is SRPM2 TI LFA computation and fragmentation caveats. So if anyone can think of, after reading through the draft, any caveats related to TI LFA computation at the PLR node to the merge point, and any through that bypass loop, and any fragmentation caveats related there. Another question that we have, and we want to get feedback from the working group as well, is SRPM2 SRv6 source node encapsulation and any fragmentation caveats there when that happens. And then the last question is the SRPM2 binding SID path computation caveat. So on the source node, when the SR policy candidate path is bound to the forwarding plane, then the binding SID is popped, and then the labels are pushed onto the label stack, or in the SRv6 case, the SRH header and the SRv6 packet is pushed onto the label stack. Are there any computation caveats that we're missing? We just want to make sure that we cover all our bases in the draft. And any questions or comments, we really appreciate any feedback on the draft. Next slide. So this draft, we feel, is fairly straightforward. We'd like to take any comments to the mailing list, but we would like to ask for workgroup adoption on this draft. Thank you.
Any comment on questions?
Did that sound any
Apologies
better?
for the lights. Don't know what's happening.
No question.
Go on to the next.
Okay, thank you very much, Gayan.
Okay, thank you.
So we are now moving to Service 6 on MPLS interworking from Swadesh.
Hello, everyone. I am Swadesh Agarwal from Cisco Systems. This document describes the SRv6 and MPLS interworking procedures, and I present this on the behalf of all my co-authors. Next slide, please. Yeah, this slide shows the simple view of the interworking scenarios. In the green, we are showing the SRv6 domain. In the orange, we are showing MPLS domain, and the dashed oval is for the interworking functions has to be executed. The document divides the problem into two set of things. One is the transport interworking and the service interworking. In the transport interworking, what happens is, and from the end-to-end, from the service point of view, it's running either SRv6 VPNs or the MPLS VPNs. And since end-to-end is an SRv6 VPN, we need to provide a transport reachability to locators. And that's what we call SRv6 over MPLS. We do interworking functions for the locators on these dashed oval boxes. And when we have a MPLS VPN's edge services running end-to-end, we need to provide interworking procedures on those dashed boxes, ovals, on whenever the data plane changes, and that happens for MPLS or an SRv6 domain. And the last case we cover is service interworking. In this case, we have to provide connectivity between SRv6 VPN and MPLS VPN, and you need to do an interworking function on some interworking box. Next slide, please. So for interworking functions, the document describes new behaviors. One is the n.dtm. What this behavior does is it decapsulates an SRv6 packet and look up it's carrying an underlying label below it, and it looks up the label in the MPLS table. And we will see how this is used in as we go in the procedures. And you can see the pseudocode in the draft. Next slide, please. And the DPM behavior is it's a decapsulation and push the label associated with the SID. And again, it is used here. We can see how it will be used in our slides as we go through this. And the pseudocode could be referred, again, can be checked in the draft. Next slide, please. So these are the hidden behaviors we are defined. So what happens is when the h.ncaps is applied to an MPLS label stack, that's what we call h.ncaps.m. And there is both the regular behavior and the reduced behavior for it. Next slide, please. So SR policy is bound to a binding SID. So in the procedures, the SR MPLS label can be bound to an SRv6 policy, as well as SRv6 SID can be bound to an SR MPLS policy. So we call these in the draft as interconnecting binding SID, and we'll see this concept is used to provide those interworking functions in the next slide. Next slide, please. As already mentioned, when the services are of the same type end-to-end, and we need to provide a reachability either to if it's SRv6 VPN to a locator, or if it is a MPLS VPN services to a PE loopback. So what this draft does is it extends the two well-known transport procedures to provide this interworking, to create this interworking control plane. One is a SRPC based, which can provide both the best effort as well as the intent aware. Another one is the BGP interdomain routing, which is right now described for best effort, but we'll define it for the intent aware based on BGP also in the future versions. Next slide, please. So just to go over the procedures, the legends used are the green boxes are SRv6 capable, and it shows how the locators have been referred in that. And the orange boxes are MPLS capable boxes, and then the orange and green bar are capable of both MPLS and SRv6. Next slide, please. So we see these are SRPC based procedures. So let's say between 1 and 10, we are running the SRv6 VPN services. And it's been advertised by the 10, learned by the 1 or VPN service. And what the endpoint or the locator we want to reach is of a node 10. B10 is the locator we want to reach. It's a multi-domain network. One doesn't know how to reach. One requests an SRPC for a certain objective or a constraint for a path to 10. SRPCs look at the constraint. It figures out the, let's say, node 2, node 5, and node 8 are in the path to provide that objective or a constraint. But since SRPC is having the BGP LS feed from each of the domain, SRPC sees there's an inconsistent data plane happening on node 4 and 7. So what it does is, whatever interconnecting SIDs we use, the procedures we define of interconnecting SIDs, it uses that behavior. What it does is, on the node 4, since we have to take the policy through an MPLS domain, it creates an MPLS policy, but the binding SID it's bound to is an SRv6 behavior of the BM type, and that SRv6 B SID is being, once SRPC creates that policy on the 4, and that's the one which is programmed at the 1 with one of the segments which takes to the node 4 and which will get expanded on node 4 to the policy MPLS policy, and that's where the packet would transition through the MPLS domain. So if you see on the node 4, what packet received is received with the destination with the BM behavior, we will apply the BM behavior on it, and then the packet would be put into an MPLS label stack, which will take us to the, again, the objective was to reach node 5 from 4, and that's what the prefix that we have put on the packet. And then the last segment we have put is the node 7, where on the node 7, it would be a regular SRv6 domain, and it will go to the next segment, which is node 8, and of course the VPN segment, which will take to the node 10. So that's the way interconnecting binding set is used to provide that 6/m reachability through SRPC. Next slide, please. So it is similar behavior. It's a similar operations that I have already explained for 6/m. The only difference is here the edge services are MPLS VPN services. So we need to create this SRPC request is for the P loopback. It's called for a certain C, E, which is an MPLS in the MPLS case. Here on the node 4, what we are doing is we are putting an SRv6 policy, because middle domain is an SRv6 domain, that policy, but it is bound to an MPLS BSID. And that MPLS BSID that is programmed for the policy on node 4 is programmed as one of the segments on the node 1. So now what happens is when the packet leaves 1, it is going through the segments in the left domain. On the node 4, it is expanded to a SRv6 policy with the next header being 137 because it's carrying an MPLS payload below 8. And then the packet will be reaching the node 7, and the regular MPLS operations will happen from there onwards. Next slide, please. So these are, we have covered the SRBC PC-based procedures where PC was aware of this interworking procedures and was creating those using the interconnecting sets to create those pass through to the different type of data plane. But similarly, BGP interdomain procedures can be used. So in this, again, it's a scenario of 6/m where the services are SRv6 VPN services. So now what we need to do is when 10 advertise the service to node 1, 10 will also advertise the locator through locator to node 7, from node 7 to node 4 to node 1. When it's advertised between 7 to 4, what you need to do is it's a regular IPv6 prefix over an LU MPLS transport. So we can use the 6PE procedures between 7 and 4, and that's the way traffic will flow from 1 to 10. Next slide, please. So this is a case of MPLS being in the edge. That means it's an MPLS VPN services. So we need to provide a reachability to node 10 that has to be learned by the node 1, which is learning the services from the 10. To provide that reachability, today we know BGP 3107 procedure seamless MPLS is used, where what will happen is on the 7, we will allocate a regular BGP LU label, but along with that, we will advertise an SRv6 set of the behavior DTM, which was defined earlier, right? And that would be learned by the node 4, and node 4 will advertise this BGP LU further to node 1. So for node 1, it's a regular MPLS VPN put into BGP LU LSP, but on the node 4, yeah, we will do swap operation for BGP LU LSP, but along with that, we will tunnel the traffic to node 7 with the DTM behavior. What it will cause is we are carrying a BGP LU label below that SRv6 set. So on the node 7, we will decapsulate the packet, do the lookup of the BGP LU label, and send to node 10. So that's the way we'll provide end-to-end reachability over the SRv6 domain. Next slide, please. So these are the cases of transport interworking where we were trying to provide a reachability towards the service endpoint. But in this case, what we want to, this is a service interworking where we want to provide a connectivity between MPLS VPN and SRv6 VPN running on the node 1 and node 7. So what happens in this case is these are working on the existing gateway procedures. What happens is on node 4, we have a service awareness because we want to terminate both the services as well as the underlay. So since we want to terminate both, what we can do is we can have a service awareness on node 4. So whatever is destinations, VPN destinations are learned from the SRv6 domain, they are put into the WRF on the service box node 4 and then reoriginated towards the MPLS side. So there is MPLS VPN and SRv6 VPN. And on the service box, there's a WRF IP forwarding, which is when you receive a traffic from one side, you decap, you do an IP lookup, and then you get the encapsulation for the other side. And that's the way that we provide the interworking solution for this scenario. Next slide, please. So this is the last case where instead of having a service awareness on the node 4, what we can do is on the interworking box, we can do a translation. That means a VPN label could be translated to an VPN's SRv6 service set, or the SRv6 service set can be translated to a VPN label using a procedure similar to interest option B, doing a next hop self on that box. Next slide, please. Yeah, summary is this draft was presented, first published in 2018, and it has the data plane and the associated control plane procedures. It defines a new behavior, DTM and DPM, as well as introduce the concept of interconnecting binding sets, and it uses how to pass through a data plane which are not consistent. It relies both on the SRPC and BGP based solutions. Next slide, please. Next slide, please. Yeah, so one thing we have done is from the last IETF, we have moved the BGP protocol extensions that we have to a separate draft, so it can be reviewed in the BEST working group. And this is done for both for the independent review as well as future applicability for the other use cases, as well as we have expanded on the interest option B like procedures for the service interworking. Next slide, please. Yeah, we would like the working group to review as well as adopt this draft. Also, one thing more, there's another transport interworking draft being there in the spring. We are working with the co-authors of that draft because there's one similar behavior being defined to see how to move forward on that. Thanks.
Okay, Dhruv.
Oh.
Jeff, you got to put yourself on the list.
Hi, Swadesh, very good presentation. Thank you. One quick question about the PCE part. Currently in the document, you are focusing only on a single PCE case. In PCEP working group, we have one more document called stateful interdomain, where how the PCs can cooperate with each other to set up this kind of part. So just have a look at it. I hope that the solution can work for interdomain cases, like where multiple PC managing multiple domain cases as well.
Sure, I've been looking at that, and probably we can get back on
Thank you.
what we can do.
Jeff?
Jeff Control, Microsoft. So the draft notably misses operational part. How do you deploy the stuff? How do you operate it end to end? And I mean, amount of bugs when you're going to deploy this, it's just scary, right? So it would be really good to see sections that identifies how do I trace when I traverse different encapsulation, different domains, when I replace seeds by labels and so forth, right? It's completely missing in the draft.
So you're saying the operational aspects?
Absolutely.
Sure, we can look into it. Thank you. Update. Thanks.
But you should put yourself on using the tool, but just state your name at the microphone, please.
Okay, let me do that right now. Yes.
Go ahead.
LinkedIn. To the point which Jeff was making, I think there should be a separate operational draft on.
Yeah, we can look into it. That's something. Let's look and get that part covered.
Okay, George.
Hey, Swadesh. Jorge Rabadan, Nokia. So you said that there is another draft in BEST for the pure BGP procedures for the
signaling aspect too, because we are extending to carry these new behaviors in the BGP, in the BGP transport layer like BGP LU or in BGP IPv6. So we have put earlier that was in this draft, but to have a future applicability as well as to get it reviewed by the BEST, we have put in those signaling aspect, we have put in separate draft, and the architecture and the procedures are still kept in this draft.
But also for the option B section, because at the moment it's only covering the LU part, right?
No, option B is for the services, right? We can do next hop self on the interworking box where SRv6 service set can be mapped to a VPN label and the outgoing LSP, and same on the reverse direction, right? So it's using a DPM behavior to achieve it. Right. So it's a next hop cell for the services, not for the transport.
Okay. So you're saying there's no need for extended procedures in the BEST draft for the option B?
We can look into it, but it's just because option B is already defined in certain aspects. This is more of using those procedures to create this. But the behavior is a new behavior, DPM. That's the reason we have put it out, so that everybody knows we have to use a DPM behavior. We have to push a label, a stack of labels when I receive a SRv6 set. That's the reason we have put it out. Otherwise, from control plane, I still feel existing procedures should work. It just some data plane and update to that.
We can discuss.
Sure.
Thank you.
Sure. Thanks a lot.
Thank you, Swadesh. Next is SR Policy Group from Lian.
Oh, okay, thank you. Hi, this is Lian again. I'm talking about the other topic, SR policy group. Next, please. This slide shows the requirement and the application scenarios. The initial requirement is in the multi-storage scenario of the single user. Different storage flows of the same user have different requirements on the forwarding quality of the network. So different traffic is expected to be forwarded through different passes and use different network resources. Taking the left picture as an example, there are two completely isolated VPN tenants, VPN 1 and VPN 2. They are both multi-point to multi-point access. And the VPN 1 has 3 different types of services. VPN 2 has 2 different types of services. Each service has different quality requirement. First, from the picture, you can see that all the traffic belongs to the same VPN. It's expected to be managed in a unified manner. So here, we steered the traffic into one SR policy group. So the traffic belongs to the SR policy group who have different sources and different destination addresses. And the next different type of sources traffic under the VPN can be steered into different policies, which is based on the parent policy. The traffic has a specific source and destination address. Next, please. This is the terminology which is defined here. First, the SR policy and the parent SR policy are defined in RFC 9256 already. And the new concept of the SR policy group is newly proposed here. And generally speaking, it is an instantiation of a set of parent SR policies. These SR policies have different destination endpoints and the same service forwarding module. And it represents a set of passes with different forwarding requirements and composited by different parent SR policies, which have the same color but different destination endpoints. Also, the mapping relationship between the flow characteristics and the color value of the SR policy path should be established in the policy group. And it can get the flows with different SLA requirements to the SR policy with different colors. Next, please. This is the identification of the SR policy group. An SR policy group must be identified through a color attribute. This color is an unsigned non-zero 32-bit integer value, and it corresponds to the color attribute of the BGP route published by the endpoint. And the third one, second, different service qualities use different color values. The next sentence is also talking about the mapping relationship between the flow characteristics and the color value. The same with the previously slides. So next, please. The relationship of the policy group, parent policy, and SR policy is shown as the pictures. First, in simple terms, SR policy group contains one or more parent SR policies, which have different destination endpoint. And the color of the policy group should be same with the parent SR policy, but different with the SR policy. Next, please. This slide detailed the process of the traffic steering using the SR policy group. For the egress node, which published the BGP route, it will associate the BGP route with the color extended community attribute. And for the ingress node, first it will match an SR policy group using the color extended community attribute in the BGP route. And then next, it will match parent SR policy under the previous policy group using the next hop in BGP route. And then it will match an SR policy using the flow characteristics. Through the three steps, finally, the flow is steered into one specific SR policy. Next, please. This is an informational module of the upper logic. From this picture, you can see that there is one SR policy group, PG1, which is with the color 1, and it contains two parent SR policy, PP1 and PP2, and they have the same color 1 with the policy group PG1, but different endpoint, E1 and E2. And each parent SR policy contains three threads corresponding to three different policies, which is with the color 100, 200, and 300. This picture shows the basic logic of the relationship. Okay, next please. That's all. This is the 0.0 version of the draft. So welcome any question or comments. Thank you very much.
Okay, Katan.
Ketan Talavlikar, Cisco. If you could go back to the previous slide, Bruno. Yeah. So one question: SR policy group, which is a new new thing that is being introduced here. Does this belong on the head end, or is this something that's on the controller?
Do you mean that the SR policy group does have any head endpoint?
So it's at the head end. Okay. So I'm not able to see what is the benefit that this group brings. It would be good if the draft could be updated to clarify what cannot be done or achieved with what we have today before, and
Okay.
so therefore we know why we need this new construct.
Yeah, so
Okay,
Chair, I'm Wu Qiangcheng, also the co-author of this draft. I would like to answer the question. So, firstly, I think the policy group will not introduce any new header or new change to the data plan. And the second one, we use that based on maybe controller or some other network management system, so that is logically module to organize the hierarchical services. So we just talked about the hierarchical network slice. So when we use the SRv6 policy to implement the hierarchical slicing, those solution can be used at that application scenario. Hello?
I still do not get the actual value or what I need to implement as a as an implementer. So maybe some clarity more, some more clarity in the draft would help.
Yeah, I think the important value is that it's a help to organize those different policies for such as the same user or the same kind of service. So if you can use those concepts, then you can very easy to set up the hierarchical services based on SRv6 policy.
Very last bit. Sorry for taking the time, but we have all kinds of template and hierarchies in all the vendors config models, right? The question is here, why standardize it? You can do whatever you want in your controller or head-end implementation. If we are standardizing, it should bring some functional value, and that's not clear to me. Thank you. I'll end here now.
Okay, Boris.
Hi, this is Boris. A very short question, guys. Maybe I missed. We have two colors here. One color per SR policy group and second color for SR policy inside this group. So how these two colors resolution will be done? It's not quite clear.
I think at the same library, we just use one color. So such as at the SR policy group, we just use the same color for one parent policy. But within the SR parent SR policy, the different services may have a different color. So that it's similar to the hierarchical queues.
Okay, we'll look into the draft. Thank you.
Thanks.
Okay, we'll move on to the next presentation.
Hello. Can you hear me?
Yes, we can hear you. Go ahead.
Oh, okay, thanks. Good morning, everyone. This is Wei from China Mobile. I will present the draft network resource programming with SRv6. Next slide, please. The concept of network resource partition is introduced in draft IETF network slices. as described in section 6.1 of that draft. NRP is a collection of resources in the underlying network. NRP consists of a subset of the buffer, queuing, scheduling resources on each of a connected set of links in the underlying network. And RFC 8986 has defined a set of well-known SRv6 endpoint behaviors. But those behaviors are not associated with a set of NRP of the links for slices or slice aggregate. So this document defines a new SRv6 endpoint behavior, which can be used to associate with a set of NRP. For example, the dedicated queues resources or layer 2 logical sub-interfaces. We called end.nrp. Next slide, please. The uses of the end.nrp seed. This end.nrp seed is mainly used to steer traffic forwarding through the associated NRP. By using the end.nrp seed to build its segment list, the SRv6 policy have the capability to program network resources and achieve strict SLA guarantees. For one HP link, multiple end.nrp seed should be allocated, each of which is associated with a subset of link resources, such as dedicated queues, layer 2 logical sub-interfaces, and so on. Let's see an example as shown in the picture 1. For the P1 node, the link resource from P1 to P1 has two NRPs. One is GE100.Q1 and another is GE100.Q2, which are two dedicated queues on P1 physical interface GE100. Also, two end.nrp seed are allocated to those two NRPs. This means that for P1 node, the end.nrp seed A:1:11 is associated with NRP GE100.Q1 and indicates to forward traffic to neighbor P1 via this NRP. And the end.nrp seed A:1:22 is associated with NRP G100.Q2 and indicates to forward traffic to neighbor P1 via this NRP. When an SRv6 policy uses the end.nrp seed to construct its path, such an SRv6 policy can provide strict SLA guarantees to customers. Next slide, please. This is the processing of end.nrp behavior. The end.behavior behavior is a variant of end.x behavior defined in IFC 8986. Any seed instance of end.nrp behavior is associated with two sets, J1 and J2. J1 is one or more L-SAN adjacencies. J2 is NRP of J1. When N receives a packet that's destined to S, and S is a local end.nrp seed, the line S15 of the n.x processing defined in RFC 8986 is replaced by the following. Submit the packet to the IPv6 module for transmission to the new destination via a member of J1 using the NRP identified by J2. Okay, next slide, please. This is an use case of the end.NRP behavior in the SRv6 list line scenario. In this use case, there are two customers with different list line requirements from P1 to P2. One is a list line with 1G bandwidth with strict SLA guarantee. Another is a list line with 2G bandwidth with strict SLA guarantee. So the controller will build two SRv6 policies to meet the list line needs of those two customers. First, it calculates SRv6 policy paths based on SLA. Assuming that both paths are calculated as X1, X2, X3. Secondly, the controller cooperates with the network nodes to complete NRP reservation and the end.NRP seed allocation along the SRv6 policy path. Also, take node P1 as an example. The two different NRPs, such as two dedicated queues, are partitioned from the network resources of the physical link X1. And a corresponding end.NRP seed is also assigned to each of those two NRPs. The results as shown in the table 1. The seed A colon 1 colon 11 is associated to NRPG 100.Q1, and the seed A colon 1 colon 22 is associated with NRPG 100.Q2. Next slide, please. Similarly, the NRP reservation and NRP seed allocation are completed on X1, X2, and X3 links. Finally, the controller uses the corresponding end.NRP seeds on link X1, X2, and X3 to build the seed list of SRv6 policy paths, as shown in the picture 2. The path for SRv6 policy 1 is A colon 1 colon 11 and A colon 2 colon 11 and A colon 3 colon 11, which satisfies the requirement of the customer 1. And the path of SRv6 policy 2 satisfies the requirements of customers 2. Oh, okay, next slide. Next slide, please. Okay. In this use case, the traffic from customer 1 will be forwarded to P2, while the NRP previously reserved for the per hop link on the SRv6 policy 1 path, and thereby providing customer 1 with an end-to-end 1G bandwidth resource for list line services with strict SLA guarantee. Next slide, please. Okay, that's all for my presentation. Any question or comments?
Thank you. Any question or comment from the room? Yes, Ryan?
Question. I was wondering, how are you mapping the, it seems like there's a mapping between the NRP, I guess, when the controller is provisioning the flow, I guess, to QoS, because you mentioned queuing. So I was just how mapping is happening, as well as if you have that, let's say on the box, you probably have your standard queuing set up, but now there's another layer of queuing that's set up with the with this programming, and I guess how that works. I guess the inner workings of that. Thank you.
Okay, I try to answer your question.
So yeah, maybe I'm also the co-author. I would like to answer the question. I think as you just mentioned, the NRP maybe existing in the controller for the provisioning, as well as how to attach the NRP to the forwarding layer is a question. And it's very hard for controller to manage the dedicated resource in the forwarding layer. So combine the NRP in controller modeling and the under NRP behavior, it will to set up some good solution. Very simple. You can use such as ISRv6 policy, and as well the dedicated resources in the forwarding layer can be attached. It will help operators to support the high quality list line, something like that. Thank you.
Thank you. It sounds like, would it be like a layer of like a hierarchical QoS almost? I guess like you have a layer of QoS per NRP, similar to like hierarchical QoS. Thank you.
Thank you. Yeah.
Thank you. Next and last presentation is segment encoding procedures for multicast VPN service in native IPv6 network.
Okay. Hello, everyone. I'm Wei Wang from China Telecom, and I will introduce our draft on behalf of the co-authors. And next slide, please. Next slide, please. Yes, we proposed this draft to define a new segment. We called it endpoint and VPN to contain the VPN custom informations. And this segment can be used to distinguish traffic from different customers. And it can, and with this segment, the VPN multicast group address allocation can align with the unicast IP VPN address allocation. And the implementation of this solution is similar to router and VPN, and it can also compatible with beer and other technologies. And next slide, please. Yes, when a customer wants to join the multicast group, the egress-P is connected to will generate an endpoint and VPN according to the VPN customer information and send the segment to ingress-P. And on ingress-P, it will maintain a mapping table of endpoint and VPN and VPN customer information. And the generated endpoint and VPN will be inserted into the table. And when CE sends a multicast packet to ingress-P, the ingress P will encapsulate the packet with a header according to the endpoint MVP mapping table. And the destination address will be set to the endpoint MVPN. Then the packet will be sent to the responding egress Ps, and the behavior on P routers depends on the generation method of the multicast tree. And finally, the egress P will decapsulate the packet and transmit it to the corresponding Cs. And next slide, please. Yes, this is the encoding of endpoint MVPN, and it will come first to the IPv6 multicast address. And we define we define the highest bit in FF1 as the V bit, which means the VPN multicast bit. And when this bit is set, it means the multicast group address is an VPN segment. Otherwise, it is a common multicast address. And the network prefix field will carry the customer's RD value when the V bit is set. Otherwise, the information carried in this field should be determined by the other bits in FF1. And the group ID carries the information of customer group. Next slide, please. Yes, this is the generation procedure of endpoint MVPN. When an ingress P generates the endpoint MVPN segment, it will firstly extract RD and multicast group address of the customer and set the value of VB to 1 and set the value of network prefix to the customer's RD. And then the ingress P will set the value of group ID field according to the customer's multicast group address. If the address is IPv6, IPv4, the value of group ID will be set to the IPv4 multicast group address. And if the customer's multi-group address is an IPv6 address, the egress P will check the P bit in the address. And if the P is equal to 1, the group ID will be set to the group ID in the customer's multi-group address. And otherwise, the value of group ID will be set to a 32-bit value that is hashed from the customer's multicast group address. And next slide, please. Yes, this is the behavior on the ingress P when it received an IPv6 packet with the destination address D, and D is associated with an endpoint MVPN segment on the egress P. So the egress P will check the V bit in endpoint MVPN. If V bit is equal to 1, it will look up the endpoint MVPN mapping table according to the endpoint MVPN value and find out the associated RD and the related MFIB table T. Then it will remove the outer IPv6 header with all its extension headers and set the packet's associated MFIB table to T. Finally, it will submit the packet to the egress MFIB lookup for transmission to the new multicast downstream. And if the V bit is equal to 0, the ingress P will set the packet's associated FMIP table to global FMIP and submit the packet to the egress FMIP lookup for transmission to the new multicast downstream. Next slide, please. Oh, yes. And since this is the first time for us to give the presentation of this draft, so we hope we can get some comments or suggestion about it, and we will revise this draft accordingly. Thank you.
Thank you. One question. Did you ask a slot at the best working group? Did you ask for a slot at the best working group to present it? Or?
This time we don't apply the slot time.
Maybe it would be good to ask to present for next meeting because it's heavy on VPN and multicast VPN.
Yes, we maybe we will presentation it in next IETF meeting. Thank you.
Sasha?
Hi, I'm Sasha Weinstein from Ribbon. I had looked up the draft before the presentation and sent an email to the authors and the work group. It seems that the solution proposed in the draft only can work with egress replication as the provider tunneling technology for MVPN, because the structure of the end.mvpn SID includes the route distinguisher of the multicast VRF in the egress PE. Route distinguishers in many, if not most cases, are specific to each egress PE. For instance, if you use type 1 route distinguishers, they would include the something like the router ID of the egress PE as part of it. And therefore, in order to work, this proposal would require the egress PE to send a dedicated packet to each egress PE where the specific MVPN service is instantiated. At the very least, I think that this should be explicit. If my understanding is correct, I think that at the very least, this should be explicitly specified in the draft. If I have missed something, I would really appreciate explanations.
Yeah, I think you have a good question. Actually, for multicast scenario, the RD value for all of the egress PE should be set one unique value. Oh, okay. Then our draft just describe the format of the ordinary VPN for the multicast service, and the multicast service, the multicast address must be the same for the multicast service. Okay.
This is definitely not what the normal MVPN behavior suggests. And in any case, if you start, say, from the unicast VPN service that you wish to upgrade to multicast VPN, you don't change the route distinguishers. But in any case, if this is the assumption of the draft, it should be stated explicitly because maybe I have missed it, but I have not seen anything like that in the text. Normally, in layer 3, and that's why I think that if you present this draft at the best work group, where it definitely should be presented because it includes the BGP parts, the same question would be raised.
Yeah, okay, we will adopt your comment. But I think even for the unicast solution, the RD can be set differently or uniquely. So I think we should express in our draft or in our next practice note, express explicitly that the RD value should be same for the all the equal PE in one VP.
Gayan, if you can have a short question, please.
Sure. I did just a quick question. Does this draft, does it follow like the MVPN procedures, RFC 6513 and 6514, using like Leaf AD to discover the endpoints, like the auto discovery piece, or this is completely separate from any MVPN procedures? Also, I do agree that this seems like it's more in line with like ingress replication and not any other PTAs. Thank you.
You can comment briefly. Go ahead.
Hey, John, I think the current solution for is just mainly focus on the scenario in the native IP network. So the procedure is different from the traditional MPVPN solution.
Okay, the queue is closed and we're out of time. We are over time already. So thank you, folks, for all the presentations and for all the discussion, which is more important than the presentation in many regards. So thank you very much for your time. We'll see you on the mailing list.
I don't think we can.